Welcome to The Explainer. Today, we're diving into the ultimate shapeshifter of the periodic table, the one element that literally forms the backbone of life itself and, well, countless materials all around us. We're talking about carbon.
So let's start with a puzzle. How is it possible that the exact same element can make the soft gray stuff in your pencil and a brilliant, super hard diamond? Well, the answer is just fascinating, and it all comes down to the unique properties that make carbon the ultimate Lego block of the chemical world.
All right, so what's carbon's big secret? It all starts right here, with its atomic structure. You see, carbon has 4 electrons in its outermost shell. We call those valence electrons, and they're the ones that get involved in all the chemical action. Now, to be stable, an atom really wants a full outer shell. For carbon, that means it needs to either find 4 more electrons or get rid of the 4 it has. The thing is, both of those options take a ton of energy. It's basically impossible. So carbon's in a bit of a pickle.
So what does it do? Instead of trying to steal or give away electrons, carbon plays well with others. It shares. It finds other atoms and agrees to share its 4 outer electrons with them. This brilliant solution is called covalent bonding, and trust me, it is the key to, well, everything we're about to talk about. Think of a covalent bond like a really strong, cooperative handshake between 2 atoms. By sharing electrons, each atom gets to pretend it has a full, stable outer shell, just like those super chill noble gases. It's what makes the resulting molecules incredibly strong and stable.
Okay, so we get the idea of sharing. Let's see it in action. We'll start with one of the simplest but most important carbon compounds out there, methane. You probably know it as the main ingredient in natural gas.
Let's build a methane molecule. Picture this. You start with 1 carbon atom holding out its 4 valence electrons. Then, along come 4 hydrogen atoms, and each one only has a single electron to its name. The carbon atom generously shares 1 of its electrons with each of the 4 hydrogens. And what do you get? Methane, CH4. The carbon now feels like it has a full set of 8 electrons, its octet, and each hydrogen feels like it has a full shell of 2. Everybody wins. It's a perfect, super stable molecule.
Now, bonding with other elements is cool and all, but here's where carbon's real superpower kicks in. It's not just great at bonding with others, it's fantastic at forming strong, stable bonds with itself, over and over and over again.
This amazing property is called catenation. And honestly, the best way to think about it is like playing with Legos. Carbon atoms can just snap together one after another to form these incredibly long chains, or even branch out into complex shapes, or even loop back on themselves to form rings. It's what allows for a mind-boggling variety of molecules.
So you can go from the single carbon in methane to linking 2 carbons to make ethane, to 3 for propane, and you can just keep going. This ability to build stable chains is the absolute foundation for the entire vast world of organic chemistry. It's why there are millions upon millions of different carbon compounds out there.
And this ability to link up in different ways? Well, that leads to another one of carbon's most amazing tricks. See, it's not just about what atoms are in a material, but how they're arranged. The exact same element can create materials with wildly different properties just based on their internal structure.
These different structural forms are called allotropes, and carbon has some of the most famous and fascinating allotropes known to science. Which brings us right back to that question about pencils and diamonds.
Okay, check this out. In a diamond, every single carbon atom is locked tightly into a rigid 3D grid, bonded to 4 other carbons. This structure makes it the hardest natural substance we know of, and it won't conduct electricity. But then you look at graphite. Here, the carbon atoms are arranged in flat, hexagonal sheets, kind of like molecular chicken wire. Each carbon only bonds to 3 others, which leaves 1 electron free to roam. Those free electrons make graphite a good electrical conductor, and the sheets can slide over each other, which is why it's so soft and slippery. Same atoms, 2 completely different worlds. So we've seen carbon's incredible structural versatility. Now let's see how those long carbon chains are put to work in something we all use every single day: soap.
You have to understand, a soap molecule basically has a split personality. It's got one end, the head, that is hydrophilic. It absolutely loves water. And then it's got this long tail made of a carbon chain that's hydrophobic. It's terrified of water, but it loves oil and grease.
So, when you wash your hands, this amazing microscopic drama unfolds. The soap molecules swarm any speck of oily dirt. All those oil-loving tails dive right into the center of the oil droplet, burying themselves inside. Meanwhile, the water-loving heads all stay on the outside, facing the water. They form this perfect little sphere called a micelle,
with the oily grime trapped right in the middle.
This clever little structure works like a tiny getaway car for grease. The outside of the micelle is water-soluble, so even though the oil is trapped inside, the whole package can be lifted off your skin and rinsed away with water. It's perfect chemistry in action.
And you know, this is also why modern detergents often work better than old-fashioned soap, especially if you have hard water. Hard water is just water with a lot of calcium and magnesium ions in it. Those ions react with soap to form that nasty, insoluble gunk we call soap scum. But detergent molecules, they're designed differently, so they don't form that scum. They just keep on cleaning no matter how hard the water is.
So when you step back and think about it, from the simple act of sharing an electron to building endless chains to forming the very basis of technology and life itself, carbon's versatility is just staggering. It really makes you wonder, doesn't it? With this ultimate building block, what new materials, what new technologies are just waiting out there for us to discover?